Hello, I'm Wyatt. I created the quiet board for my ISU Robotics and Communications final project, and today I'd like to give you a little presentation about how it works so that you can better use it in your projects. So let's get started. Quiet 1101. So this is the beginning of a series of videos I plan to put out that will describe tips and tricks and ways to use the hardware and software. That'll be beneficial to you, hopefully, so you can understand it and be able to do more with it. So to start, we have a hardware overview. We'll be discussing some of the schematic and the unique PCB features that are used on here to make it quite a flexible little device that's pretty easy to use with LabVIEW, Visual Basic, or if after you've been through a little bit of assembly, it's not too bad to use. But today is just the hardware. So first things first, block diagram. What do we have here? We have 8 digital inputs, 8 digital outputs, 4 analog inputs, 2 PWM/analog outputs, and 4 different types of communication ports that are available. So moving on then, second thing second, digital inputs. All of the inputs on here are 5.5 volt tolerant, even though the PIC 18F46J53 is only a 3.3 volt chip. It has these 5.5 volt inputs that make it much easier to use with your typical TTL level logic. There's also a button for each digital input that can be soldered on that is isolated by a 10k ohm resistor and has a 10k ohm pull-up resistor as well. These are useful for troubleshooting and for an interface into any of your software that you have hooked up to this. However, these buttons are overridden by active signal, so if it's pulling it high or pulling it low, pushing the button won't do anything. Also with that 10k ohm resistor, it is a pretty high value, so you shouldn't have any problems, but it could feed back into your circuit and cause some issues if you don't look at it right. Next up is our digital output. So these have a lot going on here. We have our LED indicators, and they have a jumper. Let's see if I can do a little drawing here. Maybe, yeah. We have a jumper right here that can be used to disable and enable all of your LEDs. If you don't want them on, or if you need a little bit extra current to get up to the full 25 milliamps, that's possible. You'll want to unplug this jumper. Otherwise, I leave it in because it's a good status indicator of what the PIC's trying to output. There are 2 different drive methods on this board. You have direct drive, which is used by connecting the jumpers as seen above the optocouplers, and it gives you very high speed responses to all of your input requests. Optionally, you also can use the optocouplers if you need higher currents or larger voltages than the 3.3 volt output of the PIC. I would avoid using the optocouplers if possible. They're slower and they're expensive to use. Unfortunately, because of pin requirements, the I2C port and the programming port, as you can see there in the middle, are both tied into the digital outputs. This usually isn't a problem for most projects, but sometimes it will be a bit of a hindrance. Next up is our analog inputs. They are buffered analog inputs, so you can see we have a operational amplifier on there, and it has a gain of 100k divided by whatever you set up as your R48 plus 1, because it is a non-inverting amplifier. To help get rid of that plus 1 in there, you can use the potentiometer to give yourself an attenuation or a gain of 0.5 through there. And you can also use that if you want to put in a signal larger than 3.3 volts, you can use that to attenuate the signal such that your output of the operational amplifier will only range between 0 and 3.3 volts. There is a jumper. JP4 in this illustration is used to give yourself a dedicated input. This will override whatever you have coming in, unlike with the digital inputs where the incoming signal overrides the buttons. In this one, the jumper will override whatever your input is. And it's useful, so you can use a little screwdriver and make sure your analog input is working. You also, on channel 4, there's room for a photoresistor that can be used in 5th semester to help with one of the labs in there, or if you just, any light project can be fun to do, you know? Oh, I forgot to slide through here. Did I miss anything? Nope. Nope. No. Perfect. Okay. Next is our PWM/analog outputs. Each one of these 2 channels has an LED indicator with brightness to show you a little bit of what's going on there. There is a direct drive PWM output. It's on the outside rails of your analogs. And these are really good for H bridges, or if you need to do a variable motor speed, this is the place to do it. Don't use your digital outputs. The digital outputs are much slower, which is more inefficient, and this will give you better resolution as it is. There also is the analog output section where we have a low pass filter consisting of R50 and C50 in this depiction that will give you more of an analog level out. I believe these outputs are capable of 8 milliamps at 3.3 volts max. Low pass, the signal is just the low pass of the PWM, so I don't know an application where you could use both the low pass output and the PWM at the same time. It'd be interesting if someone came up with that. I'd really like to know about it. That'd be pretty cool. The last part on here that I'll mention is that we have 4 different communication types. We have USART or UART, SPI, I2C, and USB. These are a bit beyond the scope of this presentation, so I'll leave it at that. Next up is an overview of the PCB layout and some unique features such as the surface mount jumpers and the output header. As you can see here, I have in the light blue the digital inputs on the left side. On the top we have our analog inputs. We have our analog outputs on the right, which makes that little C shape. So that top left pin is an PWM output, and the bottom left is a PWM output. And then the 2 middle pins, not the center one, but the 2 middle ones are your low pass buffered outputs. And then we have our digital outputs in green. One of the interesting parts of this board, and this part that helped me out a lot when doing the PCB layout, was the surface mount jumper. It's a little tiny piece. It's only about 4 millimeters by 8 millimeters in dimensions, and it took out a large 0.2 inch jumper that was sticking way out of the board and made everything look really messy, and it brought it down to this little tiny piece that normally people only use one time anyways, and it'll allow you to connect different parts of the board together, usually to share power or to enable the direct drive on the outputs. The best way to bridge this is with really poorly flexed solder or just a little tiny snippet of copper, and you put that on there and solder it on, and it will usually work pretty well. One very confusing part is the digital output section. Each pin has a reason though. On the furthest left side, there's a column of surface mount jumpers. When they are bridged, the output of the PIC is directly inserted onto the 2 leftmost columns of 0.2 pitch headers. In applications that require optocouplers, the leftmost column is intended to be filled with a single inline resistor pack to provide the pull-up necessary. The input supply for the resistor pack is any of the ISO power pins located in the middle right column or the topmost pin of the middle left column. The remainder of the middle left column is dedicated for the output signal, whether direct or indirectly driven. The 2 rightmost columns are for ISO power and ISO ground. This allows a generic 3-pin servo to be connected directly to the board, and to better accommodate the power needs of the servos, the bottom row was designed to provide a very direct power connection for these motors. The bottom row can be used to supply the whole board by use of JP18 on the backside. Be careful not to overvoltage everything though. Conclusion: this hardware is pretty flexible. You can either populate the whole board, which you normally don't need to do, or you can only populate a few parts. You could put like the processor and the oscillator on there with your buttons, or you could just use the outputs. It's very flexible. It's good to have an idea of what you're trying to do before you make this so that you don't end up putting on a bunch of stuff that you're not going to use. And it's always good practice to do a bit of circuit analysis to make sure that you're not going to have any conflicts between your circuits and these circuits on the quiet board. Thank you very much for joining me on this quick video. Hopefully you enjoyed it. I know I did, somewhat.